This is the screencast for section 3.6, example 6. We're going to find the derivatives of parametric equations or parametrized curves. There's a, I think, rather logical rule for taking the derivative of parametric. Parametric is a function of t. X is defined as a function of t, and y is a function defined by t. If you want dy dx, you take the derivative of y with respect to t and divide by the derivative of x with respect to t, which just makes sense because that would be dy dt, not divided by dx dt, but times dt dx, which means the dt's would cancel out and you get your dy dx. So let's get started. Example 6, find the line tangent to the right-hand hyperbola branch defined parametrically by this. So I graphed that function. I gave my t value a negative pi over 2 minimum and a pi over 2 maximum. And I want to find it at the point square root 2 comma 1 where t equals pi over 4. So here's that point, square root 2 comma 1, which was found by x of pi over 4 comma y of pi over 4. Now we need to find the slope. So let's take the derivative of x with, actually I'm going to start with y first because that goes in the numerator. Let's not get ourselves confused. So the derivative of y with respect to t, derivative of tangent is secant squared. The derivative of x with respect to t, the derivative of secant is secant tangent. So dy dx is going to equal secant squared t over secant t tangent t, which then would be one secant cancels out. So secant of t divided by tangent of t. And I want to find, that is going to be the slope, and I want to find that slope specifically at pi over 4. And I can write the derivative evaluated at pi over 4 like this, dy dx, I don't know, bar, and then a little pi over 4 at the bottom. And I get that the slope is going to be square root of 2. So the tangent line is going to have the equation y minus the y coordinate 1 equals square root 2, the slope, times x minus the x coordinate, which so happens to also be square root 2. So I found the point square root 2 comma 1, and I can see that a slope of square root 2 looks like it would be tangent to this curve. Up 1.5-ish over 1. Up 1.5-ish over 1. Then now try problem number 41. Says find the equation of the line tangent to the curve at the point defined by the given value of t. So x is defined and y is defined both at parametric functions of t. And I want t equals pi over 4. So I got to find x of pi over 4 and y of pi over 4 to determine the point. So the point where these graphs will be tangent is square root 2 comma square root 2. Now to find the slope, I'm going to take the derivative of y with respect to t and the derivative of x with respect to t. Then dy dt over dx dt is going to equal my dy dx. And I want to evaluate dy dx at pi over 4. So that's going to be the opposite of the cotangent of pi over 4, which is going to be negative 1. So my equation of my tangent line is y minus the y coordinate times the slope, which I found to be negative 1, times x minus the x coordinate. So here's the point square root 2 comma square root 2, and a slope of negative 1 looks like it would be tangent.